We're jumping right into the invisible physics of our electrical grid today. In this explainer, we're going to break down exactly why replacing those massive, heavy spinning generators with lightweight, renewable energy sources creates some absolutely staggering engineering challenges. It's this wild balancing act between our clean energy goals and the raw, unbending laws of physics. So, let's get into it.
Here's the roadmap for what we'll be covering. First, the grid's inertia problem. Second, mapping grid instabilities. Third, transient faults and safety. Fourth, calculating asymmetrical faults. Fifth, grounding for grid safety. And finally, number 6, solutions for a stable grid.
Starting with Section 1, the grid's inertia problem, or the loss of the mechanical shock absorber. To really understand why modern power systems are vulnerable, we have to look at what's physically missing from the equation now. When we look at the sheer scale of the shift happening right now, it's pretty incredible. Solar photovoltaics sitting at 35% and wind power at 30% make up a massive portion of new grid penetration. Now, obviously, this brings huge environmental benefits, but from a purely engineering standpoint, it completely rewires the dynamic behavior of the entire system. And here is exactly why things are changing so drastically. Traditional grids were built around synchronous generators. Think of giant, heavy, spinning metal turbines. Those rotating masses provide natural mechanical inertia just by existing. But on the flip side, modern inverter-based resources, like your solar panels, are just lightweight power electronic converters. They have zero physical spinning mass, none. Which brings us to a crucial concept, system inertia. By definition, it's the mechanical momentum provided by the rotating masses of traditional generators. It naturally resists sudden frequency changes in the grid. Basically, it acts as a massive, vital mechanical shock absorber whenever there's a disturbance. And it's exactly what we're losing as we transition to inverter-based renewables. Take away the heavy metal, and you take away the grid's ability to easily absorb a sudden shock. Moving to Section 2, mapping grid instabilities. What actually happens when the grid loses its weight? Well, without those mechanical shock absorbers, the system gets incredibly sensitive to fluctuations. The real-world impact of that sensitivity is huge. Low system inertia is actually the leading source of grid instability, accounting for roughly 35% of the problem in renewable-dominated grids. Without that spinning weight to anchor things, the risk of sudden, severe deviations shoots way up anytime supply and demand don't perfectly align. And the physics bears this out with terrifying clarity. As renewable penetration climbs higher, the frequency deviation doesn't just creep up, it spikes exponentially. That skyrocketing rate of change means our automatic control systems have significantly less time to react before protective relays start tripping and potentially shutting off the power. Taking those traditional generators offline basically strips the grid of its raw muscle, its short-circuit capacity. That leaves us exposed across the board. We've got frequency instability caused by low inertia and harmonic issues driven by increased nonlinear power electronics. Then there's voltage instability, largely because weak grids lack the reactive power needed to support voltage during dips. Add all that to transient instability during sudden major disturbances, and you've got a heavily strained system. Section 3. Transient faults and safety. This is where instability turns into a literal physical danger. Because grid instability isn't just about your lights flickering at home. It fundamentally changes the behavior of dangerous electrical faults out in the field. So we have to ask ourselves, what actually happens during a severe transient fault when the system's strength is incredibly low? Well, when a major short circuit or a sudden loss of generation hits a weakened grid, the transient fault currents that follow become a massive physical threat to both the infrastructure and the people working on it. These violent transient faults don't just stay in one place either. They ripple all the way down the electricity supply chain, racing from the high-voltage transmission networks right down into low-voltage distribution lines, hitting substations along the way with absolutely devastating force. Which leads us to Section 4, calculating asymmetrical faults and the math behind the dangerous surge. To protect infrastructure and human life, engineers can't just guess. They have to calculate the exact mathematical behavior of these fault currents. And the math gets messy very quickly. Because severe faults don't just produce nice, smooth, alternating waves. They pack a nasty surprise called a DC offset. This is a unidirectional component of the fault current that actually delays its decay to zero. So instead of a clean wave, you get this dangerous, asymmetrical surge of energy that is incredibly difficult for circuit breakers to safely interrupt. It drastically amps up both the mechanical forces and the thermal energy released. To handle that surge safely, engineers rely on the decrement factor equation. It's a complex formula that factors in both that initial DC offset and how it attenuates over time. Using this, engineers can calculate the equivalent root mean square asymmetrical current over the entire duration of the fault. That's absolutely critical because it means they can design safety systems built for the true worst-case scenario. Section 5, Grounding for Grid Safety. Dividing the current to protect human lives. So once we use all that math to calculate that massive asymmetrical fault current, what do we actually do with it? We have to safely direct it away from the expensive equipment and, far more importantly, away from the human beings operating it. This is where soil resistivity data comes into play. Engineers use that complex data to design buried grids of ground rods placed directly under the entire substation switchyard. Their literal job is to divide that fault current and sink it safely into the earth. This minimizes any dangerous voltages that could spike on the surface right where a worker might be walking. And if you want to know why getting this math right is so crucial, look at this. In one specific calculation example directly from the IEEE BIDE, an improperly designed grid resulted in a lethal mesh voltage of 1002.1 volts. That is well above the calculated safe touch limit for a human, which sits at about 838 volts. This isn't just theory. Precise grounding math is literally a matter of life and death. Finally, Section 6, Solutions for a Stable Grid. Taming the lightweight power system. We've seen the physics of the low inertia problem and the intense math required to keep us safe. So how are we actually going to fix our increasingly lightweight grid? The answer is honestly some of the most fascinating advanced tech out there. We're now using grid-forming inverters and virtual inertia control to actively write code that mimics the mechanical momentum of those old heavy-spinning generators. By injecting power perfectly in sync with any frequency drops, these digital tools, along with advanced battery storage and even repurposed synchronous condensers, are stepping up to become our modern digital shock absorbers. But it does leave us with a pretty massive question to ponder. As our power grid becomes lighter, cleaner, and entirely reliant on digital code, will our mathematical safety nets evolve fast enough to catch the next major fault? The invisible math protecting us has literally never been more important. Thanks for hanging out for this explainer. Keep questioning and keep learning.